So here we have the primary optics. Solar slit collects angular divergence. Divergence slit collects beam spread. And the monochromator absorbs K beta and white radiation and allows K alpha radiation to pass through. For the solar slit, these slits are metal foils that are stacked in parallel with constant spacing. The spacing reduces the angular diversions of the X-ray beam and to keep it on the correct path. So by doing this, the peak asymmetry of the signal will be greatly reduced. So you will get better data. For the divergence slit, it is used to block X-rays that have too great of divergence by reducing the spread of the beam. So it is known as the height divergence. The resolution of the output is significantly increased. The divergence slit comes in a variety of sizes, which affect the peak intensity and the shape of the output. For example, a narrow divergence slit will reduce the intensity of the beam. Secondary optics can be broken down into four main parts. The selection slit, known as an anti-scatter slit, which reduces the diffusion. For the height limiting slit, a type of solar slit limit the beam, which limit the beam's height. For the receiving slit, it is the height divergence limiting slit that removes scattered X-rays that occurs from elements in the secondary optics. And for the K-beta filter, the beam passes through another monochromator just as it did in the primary optics, and it absorbs K-beta radiation and white radiation while allowing K-alpha radiation only to pass through. During the actual detection, the X-rays are absorbed by a compound that emits visible light. This process is called scintillation. The scintillation compound can be organic or inorganic crystal or an organic compound dissolved in a solvent of sodium iodide activated with thallium. A photomultiplier is used to detect the visible light from the scintillation. The photomultiplier detects photons and then produces electrical voltage, which is actual source used by the computer to create an output. For the output, we have the result for the XRD can be seen on a graph that plots intensity versus 2 theta. The peak position is 2 theta and depends on the instrument parameters such as the wavelength. Bragg's law is used to relate this position to material's peak position that is instrument independent. The spacing of the peaks can be used to define the crystal cell unit. The distance between diffracting planes of an atom is what determines as the peak position. The peak intensity is based on counts, which the number of X-rays detected for a given peak position. The intensity is determined by the atoms that are present in the diffracting angles. Thus, the intensity gives insight and the elements that are present in the sample. Also, XRD takes account into the width and the shape of the diffraction peaks by using the Scher equation. This relate the peak width and the crystal size. For a single crystal sample, if one single crystal is being analyzed, the standard setup for an XRD machine would only show one set of peaks. So when planes are aligned, like such a bisecting incident and diffracted beams, as they do at 100 and 200, so both planes are not properly aligned, like they are not at the peak 110. Then there will be no diffraction at all. For multi-crystal sample, so if there are multiple crystals present, like in powder form, then this problem can be circumnavigated. This is because the packed powder forms all the crystallite with different plane arrangements that are randomly oriented. Thus, there will be a number of crystallites with properly aligned that are properly aligned to diffract in all orientation and some point in the powder at some point in the powder. For the preparation of sample, for powder diffraction, the size of the particles should be between 10 to 5 microns. The powder is packed into a sample holder using spatula to ensure that the duvet and a glass slide is filled and the surface is as smooth as possible. For the operating parameters, so there are many parameters that need to be set to determine how well your data collection will go. These parameters have to do with the characteristics of the equipment as the slit width and settings of the powder source and how the rotation is controlled and the data is collected. So there are few common sources of error when collecting data from XRD. The most common of all is sample displacement. So this means that the sample is not in the correct place and it is not in the focus of the X-ray tube or the detector. Axial divergence can be minimized with the primary and secondary optics. Flat specimen error, a poor counting statistics can be avoided with better sample preparation. So a powder sample should be thick enough to prevent X-ray from passing all the way through it. And lastly, we have sample transparency. Can use a shift in the peaks due to the diffraction being partially displaced, and this can be lead to inaccurate peak. And like other machines, there are limitations. To get the best result, a homogeneous sample with a single phase can be analyzed. For composite or mixed materials, the limit of detection is 2%. So if there are not any elements present that it make up less than 2% of the samples, then they cannot be detected. Once a peak is collected, there must also be a reference file in order to identify what that material is based on that profile. Other limitations for this process is that there is a sizable amount of material needed in order to run the test. So if you don't have a very much of your sample, it will be a challenge or impossible to run XRD. For the application of this machine, XRD machines are incredibly powerful and can be employed to run many different types of analysis. Some of the most common uses for XRD machine include analyzing the crystal structure and even performing quantitative analysis of phase composition. It is used for finding the crystallite size and microstrain, but it can also look at the strain on a macro scale, like, or also known as the residual strain. XRD can be identify, or XRD can identify defects in sample. It is used to identify and characterize polymorphs. Texture orientation can be found and unit cell lattice parameters. Lattice symmetry can also be analyzed. It is not only can be employed to analyze crystalline materials, but also frequently used for its ability to identify amorphous materials. X-ray diffraction is extensively used in material characterization, and material characterization is necessary to identify both element present as well as the structure in order to fully define the material. Unlike other characterization methods, XRD can provide information on the elements as well as their structure, which is defined by the atomic arrangement. A material composed of only one element is called electrophile, and this can be a polymorph. A polymorph is a material with the same composition but different structure. For example, is a carbon. Carbon can either form graphite or diamond or even an amorphous structure depending on its crystalline form. So in this case of carbon, it is extremely important to not only identify the element carbon is present, but also the structure that it takes to understand what material you are working with. And so that's all for my presentation, and thank you.